You know, when you see a massive crane hoist something effortlessly, or maybe a powerful excavator delicately placing a heavy pipe, it's easy to just take for granted the incredible quiet strength of hydraulic systems.
It really is.
We're talking of a silent muscle behind so much of our world, right? Lifting colossal steel beams, precisely stacking pallets, or maybe pulling massive logs up steep inclines.
Yeah, the power is just immense.
These are systems designed for immense power, but, with that power comes an even greater responsibility for control and, most importantly, safety.
Absolutely critical.
What happens if that incredible force, just for a split second, becomes uncontrolled? The consequences, as we've, seen in real-world scenarios, can be catastrophic.
Truly devastating sometimes.
Today, we're taking a deep dive into a crucial, often unseen component that keeps these powerful systems not just safe, but astonishingly precise. We're talking about the VBCD DEA valve.
That specific one, yeah.
It's far more than just a stop switch. It's kind of the very definition of controlled movement,
Yeah.
actively preventing dangerous instability and ensuring every hydraulic action is deliberate and, smooth.
And that's our mission for this deep dive. We're going to pull back the curtain on exactly what this valve is, get into its ingenious design, and explore how it masterfully tackles some of the most critical challenges in hydraulic safety.
Okay.
This includes definitively preventing uncontrolled load descent, guaranteeing buttery smooth operation even under immense pressure, and integrating a vital shock absorber function, even if it's not explicitly called that in every spec sheet.
Right, that shock function is interesting.
It is. And you'll discover why it's absolutely vital for everything from complex, heavy-duty construction machinery to the consistent, gentle movements needed in precision agriculture. We've meticulously gathered insights from highly detailed technical data sheets, comprehensive product descriptions, and in-depth industry reports to give you a truly comprehensive, practical, and I think fascinating view of this essential piece of engineering.
Okay, let's unpack this then. At its core, the VBCD-DEEA is what's known as a double overcenter valve. Now, it's a phrase that sounds incredibly technical, maybe a bit intimidating.
It can sound that way, yeah.
So what does that really mean for those of us who aren't, fluent in every nuance of hydraulic speak? And what is its absolute main job in a hydraulic system? What problem is it fundamentally solving?
Okay, good question. Essentially, these valves are precisely engineered to control the movements of any hydraulic actuator. So that's your cylinders extending and retracting, or maybe your hydraulic motors rotating.
Got it, the moving parts.
Exactly, the moving parts, and to securely block them in both directions. Now, the absolutely crucial part, and this is where the VBCD-DEA truly distinguishes itself, is in its sophisticated management of a load's descent.
Right, when gravity wants to take over.
Precisely. Think about a heavy object being lowered by a crane or a forklift. Without a valve like this, the load's own immense weight could literally carry it away, accelerating downwards, completely uncontrolled.
Which sounds terrifying.
It is. And this isn't just a loss of control. This uncontrolled force can cause a devastating phenomenon known as cavitation within the actuator.
Okay, cavitation. I've heard that term. What exactly is happening there?
Well, cavitation is kind of like a vacuum forming inside your hydraulic lines. When a heavy load is pulling an actuator faster than the pump can actually supply fluid.
Faster than the oil can get there.
Right. The pressure in that part of the system drops so dramatically that tiny vapor bubbles form within the hydraulic oil. And importantly, these aren't air bubbles. They're literally the oil vaporizing because the pressure is just so low.
Wow, okay.
Then, almost instantly, as pressure rises again when things momentarily equalize, these bubbles violently collapse, and I mean violently. They create miniature shock waves that can actually erode metal surfaces, cause pitting in components, generate excessive noise, and lead to premature wear and failure throughout the entire hydraulic circuit.
So it's really damaging.
Extremely damaging. So the valve's core function, its main job, is to ensure a controlled descent. It's fundamentally about preventing the actuator from running ahead of the pump. Maybe imagine a car on a steep downhill without any brakes, just freewheeling and gaining speed uncontrollably.
Right.
Very bad news. The VBCD-DEA provides that critical braking and regulation. It maintains overall system control, it prevents this destructive cavitation, it avoids damage to the machinery, and most importantly, it ensures paramount safety for operators and anyone nearby.
Okay, so control and safety are paramount. What about its actual construction? What makes it tick?
Well, when we look at its key design features, the sources consistently highlight its incredible durability and robust construction. The body itself is made of zinc-plated steel.
Why zinc-plated? Is that just for looks?
Oh, definitely not just for
Uh,
looks. The zinc plating provides excellent corrosion resistance, which is crucial in harsh industrial and outdoor environments where you've got moisture, chemicals, general wear and tear. They're constant threats.
Makes sense. Needs to be tough.
Exactly. And internally, the critical moving parts, the spool, the seats, they're crafted from hardened and ground steel. This meticulous treatment ensures maximum wear resistance and dimensional stability, which is absolutely vital for maintaining the precise tolerances needed for effective hydraulic control over, hundreds of thousands, maybe millions of cycles.
Wow.
For sealing, it typically uses standard BUNAN seals. BUNAN, or nitrile rubber, is chosen specifically because it offers superior resistance to mineral-based hydraulic oils across a wide operating temperature range, and it ensures negligible leakage.
So no drips.
Ideally, no drips. Think of them as the unsung heroes, preventing those microscopic drips that can, over time, lead to major system inefficiencies, pressure loss, and potentially environmental hazards. And you'll find it's designed for straightforward inline mounting, making it relatively easy to integrate directly into existing hydraulic circuits.
Okay. Now, you mentioned the name VBCD. What about that A at the end? Is that significant?
Yes, it's actually quite significant. It's far from just a random letter. The A refers to a specific connection configuration, the way the ports are arranged, and crucially, a particular pilot ratio.
Pilot ratio. Okay, what's that?
The pilot ratio is a fundamental design element. It basically dictates how the valve performs, especially when it comes to responsiveness and achieving incredibly fine control under dynamic load conditions. This is a point we'll definitely need to delve into much deeper in a moment because it's really key to the valve's sophisticated capabilities.
All right, looking forward to that. And if we were looking at one, what does it physically look like?
Yeah, if you could visualize it, based on the product images from our sources, it's typically a compact, highly robust rectangular block of metal. Often has that slightly industrial metallic sheen from the zinc plating. You'd immediately notice various threaded ports designed for connecting hydraulic lines. Typically 2 for the supply, often labeled V1 and V2, and 2 for connecting directly to the actuator itself, maybe labeled C1 and C2. And on one end, there's usually a finely threaded adjustment mechanism, typically a screw, sometimes with a locking nut. This allows for incredibly precise setting of the valve's pressure.
And that adjustment is important.
Oh, absolutely critical. This adjustment isn't just a minor tweak. It's an absolutely critical part of ensuring the valve's safe and effective operation for a specific application and load. It truly is a robust, yet exceptionally finely tuned piece of hydraulic engineering.
So it's not just a component, it's like an indispensable gatekeeper for hydraulic movement, especially when gravity is basically trying to take over and pull a heavy load downwards.
That's a perfect way to put it. A gatekeeper.
It sounds like something that should be in every system dealing with heavy loads, but I know that's not always the case, is it?
Unfortunately, no.
Here's where it gets really interesting and maybe a little unnerving.
Indeed. It's a common misconception, maybe driven by costs sometimes, that a simple check valve is sufficient. Many hydraulic systems, particularly older designs or perhaps those built to a lower cost specification, might use what's sometimes called a Rains-Lassell-Talteventil, a pure load-holding valve.
A pure load-holding valve.
Yeah, and this is often just a basic hydraulically pilot-operated check valve. Now, this type of valve is excellent at holding a load stationary. It acts like a one-way gate, essentially like a mechanical brake, preventing fluid from flowing back until a pilot pressure signal comes along and opens it.
Okay, so it holds things fine. What's the problem?
The problem, and this is the critical flaw, is when that check valve is unblocked to allow the load to move, especially a heavy one, the cylinder or motor can retract or descend completely unbraked.
One break.
Completely unbraked. If there's a significant load acting on it, like gravity pulling it down, this uncontrolled movement can swiftly become extremely dangerous, leading to catastrophic failure or serious injury.
And this is exactly where we start to hear about that erratic, jerky motion, that chattering. That can be so problematic, right?
Exactly.
For someone seeing or hearing that in a hydraulic system, maybe on a piece of equipment, what is fundamentally going on when a system exhibits that kind of alarming behavior? And what are the real-world dangers?
You're hitting on a critical and frankly, terrifying operational issue.
Yeah.
The chattering mechanism, or the actuator literally running ahead, occurs primarily with what hydraulic engineers term ziehen de lassen, or pulling loads, or sometimes overrunning load.
Pulling loads, like gravity pulling something down.
Exactly, or inertia carrying something forward. To illustrate, imagine a powerful hydraulic winch on a logging truck. Let's say that winch is pulling a massive felled tree trunk uphill. The weight of the tree, combined with the downhill slope, becomes a significant active force pulling on the winch motor.
Okay, the load is driving the motor, essentially.
Precisely. Now, if the hydraulic pump can't keep up with the speed at which that load is trying to pull the winch cable out, or if the control valve isn't designed to actively regulate the outflow of fluid from the motor, well, what happens then is both fascinating from an engineering standpoint and potentially catastrophic in practice.
Oh.
The load, driven by gravity or inertia, pulls the actuator faster than the hydraulic pump can supply or regulate the fluid flow to it. This creates that vacuum, or that cavitation that we touched upon earlier.
Those vapor bubbles again?
Those vapor bubbles again. As the pressure drops below the oil's vapor pressure, those minute bubbles form. Then, as the actuator's motion momentarily slows perhaps, or the pump flow catches up, the pressure surges back up and these bubbles implode with tremendous force. Bang, bang, bang.
Little explosions inside the system.
Exactly. Little, but incredibly damaging explosions. This rapid cyclical formation and violent collapse of bubbles leads to a devastating chain of events. Severe pressure fluctuations, instability, wildly jerky movements, that characteristic rattling or chattering sound you mentioned, and a complete loss of smooth, precise control. The load quite literally starts to run away, maybe like hitting potholes repeatedly at high speed. It's rough, unpredictable.
Wow. Okay, so what are the consequences? I mean, besides the noise and rough movement?
Oh, the consequences are severe and multifaceted. First and foremost is the extreme danger to operators and anyone or anything in the vicinity. In applications like crane booms, for example, a hose failure or a sudden loss of control due to this running away without proper protection, like an overcenter valve, could lead to a catastrophic, uncontrolled drop of a multi-ton load.
Which could be fatal.
Easily fatal, or cause immense damage to property, the environment. We've seen tragic reports where these safeguards weren't adequately in place. Second, it can cause irreparable damage to the hydraulic components themselves.
Like the cavitation erosion you mentioned.
Exactly. Plus, as mentioned with hydraulic winches, if the load runs away, it can overspeed the hydraulic motor, causing internal damage to bearings, seals, gears, other precision components, leading to premature and costly failure. Cavitation itself, with its relentless microexplosions, erodes the internal surfaces of cylinders, valves, pumps, drastically shortening their lifespan and causing expensive maintenance and unplanned downtime.
So it beats up the machinery from the inside.
It really does. And third, there's a complete lack of control. You lose the ability to precisely regulate descent speed. This makes delicate operations like carefully placing a prefabricated wall section on a building site, lowering a delicate piece of machinery into place, or even just smoothly parking a heavy vehicle on a steep ramp utterly impossible. These tasks demand finesse, and chattering ensures only brute, unpredictable force.
Okay, so it's dangerous, damaging, and makes precision impossible.
Pretty much sums it up. And the reason a simple hydraulically pilot-operated check valve isn't enough is straightforward. These pure load-holding valves only block the load. They act as a static barrier. They do not, and importantly, they cannot, regulate the speed of descent, nor do they inherently dampen the movement under the immense dynamic pressure induced by a heavy pulling load. They just lack the sophisticated active control mechanisms necessary for safe, precise, and smooth operation in these critical scenarios.
So this is a profound problem, really illustrating that simply holding a load still isn't nearly the full picture for safety and control, especially with these pulling loads.
Absolutely not. Holding is just step one.
Given these inherent dangers and destructive forces, what exactly is the secret behind the VBCD DEA's masterstroke? What enables it to manage this energy so effectively and ensure a controlled descent, transforming what could be a dangerous freefall into a deliberate, smooth movement?
Right. This is precisely where the VBCD DEA shines and why it's so much more sophisticated than a simple check valve. It's categorized as a Senkbremsventil, which, as you might guess, translates directly from German to something like a counterbalance valve, or quite literally a lowering brake valve.
A layer and brake.
Exactly.
Right.
This sophisticated design integrates Drossel- and Dämpfungseinrichtungen, which are basically internal throttle and damping devices, directly with the pilot-operated check valve function. It's this combination, this marriage of active throttling and passive holding, that is the absolute key to eliminating those uncontrolled movements and that dreaded chattering.
So it's doing more than just opening and closing.
Much more. The brilliance lies in how its internal design actively prevents the actuator from running ahead of the pump. Instead of just allowing fluid to rush out uncontrollably once the pilot signal opens the check valve part, the VBCD DEA meticulously regulates the outflow of hydraulic fluid from the actuator.
How does it do that?
By introducing a controlled resistance to the flow, using internal spools and orifices, the valve ensures that there's always sufficient back pressure working against the load. Imagine trying to push water through a narrow pipe versus a wide open one. The narrow pipe creates back pressure.
Got it. It restricts the exit.
Precisely. This constant, regulated back pressure completely eliminates the conditions needed for cavitation to form. It prevents those destructive vapor bubbles and maintains a consistently smooth, precisely controlled descent. This is absolutely critical for precision and safety in systems like large crane booms, where a heavy load needs to be placed with millimeter accuracy, or on the masts of forklift trucks, which are constantly raising and lowering heavy, sometimes fragile pallets.
Okay, that makes sense. Now, you mentioned the pilot ratio earlier as being key. Let's dive into that. What exactly is it, and why does it matter so much?
Right, the pilot ratio. It's a crucial yet often misunderstood aspect of the VBCD DEA's performance. This ratio describes the precise relationship between the pilot area, which is the internal surface area inside the valve that the pilot pressure acts upon to push the valve open, and the pressure limiting area, the main spool area that the load pressure is pushing against, trying to keep the valve closed.
Okay, so it's like leverage almost.
That's a good way to think about it, yes, like hydraulic leverage. For the VBCD BEA, common pilot ratios we see mentioned in the sources are 1.4.5 and 1.5.5. Now, what's fascinating here, and perhaps a bit counterintuitive, is that a lower pilot ratio like 1.4.5 generally offers more precise and stable movement control.
Low ratio means more stable. Why is that?
Well, think about it this way. With a lower ratio, you need a relatively higher pilot pressure to overcome a given load pressure. This means the valve is less sensitive to small fluctuations in pilot pressure, but more responsive to the actual control input needed to manage the load. It gives you finer, more direct control.
Let me try to rephrase that. So a lower ratio means it takes more push from the control signal to open it against the load.
Essentially, yes, which means small accidental variations in that push have less effect, but your intentional control adjustments have a more direct impact. To use your earlier analogy, maybe imagine steering a very heavy articulated truck. A higher steering ratio might make it easier to turn the wheel initially, requiring less muscle effort, but it might also feel less direct, less connected to the road, maybe a bit vague.
Oh, yeah.
A lower steering ratio, on the other hand, makes the steering feel much more responsive and precise. Every small turn of the wheel has an immediate and direct impact on the wheel's angle. In the VBCD DEA, a lower pilot ratio, like 1.4.5, means the valve reacts with incredible sensitivity and stability to the pilot pressure needed to balance the load. It gives the operator that direct steering feel over a heavy, potentially unstable load.
So for tricky loads, lower might be better.
Generally, yes. This is why, for those unstable drives, where the load is constantly trying to run away or fluctuate due to its nature or the movement required, this precise, stable control is absolutely non-negotiable. It's about maintaining that exquisite balance and responsiveness even under immense, constantly fluctuating forces. Conversely, a higher pilot ratio, like 1.5.5, might improve system efficiency slightly and reduce heat generation because it requires less pilot pressure to open against the same load, but it could potentially compromise stability and fine control in certain really demanding applications. The VBCD DEA designers have expertly balanced these considerations with specific, carefully selected pilot ratios, optimizing them for different flow capacities and intended application requirements.
That's fascinating, the engineering trade-offs involved. Now, what about setting the valve? You mentioned an adjustment screw. How critical is that setting?
The setting is absolutely paramount. The sources stress this repeatedly. This isn't just a recommendation, it's a non-negotiable safety mandate. The valve's pressure setting must be at least 1.3 times the expected maximum load pressure the system will encounter.
1.3 times. Why that specific number?
It's a standard engineering safety factor. That 30% extra margin, that safety buffer, is fundamental. It ensures the valve can reliably close and maintain control even under the absolute peak load pressure it might encounter during operation, perhaps due to shock loads or inertia. It provides a critical buffer against unforeseen circumstances or hydraulic fluctuations. This 1.3x factor is what truly elevates it from just a flow control component to a certified safety device.
So it's designed to handle more than just the normal maximum load.
Exactly. It anticipates the unexpected.
Hmm.
And the process for setting this valve correctly, as detailed in our sources, like from Hydromot, for example, is a very precise multi-step procedure. And it must only be performed by trained, authorized personnel. It's not something you just fiddle with.
Okay, walk us through that. What's involved?
All right, let's break down the typical 6 steps because understanding the diligence required really highlights its safety importance. First, initial setting. You begin by setting the counterbalance valve adjustment screw to its maximum pressure setting, usually turning it all the way in. This ensures that, initially, it can hold any load it might encounter during the setup process, preventing any accidental drops right at the start.
Safety first.
Second, lift load for safety. Next, you use the hydraulic system to slightly lift the load you're working with. This is a crucial safety measure. It relieves any residual pressure on the valve and ensures the load isn't bearing down in a precarious position while you're making adjustments. It prevents injury or damage if something slips.
Makes sense. Get the weight off it slightly.
Third, deactivate hydraulics in mark position. Crucially, you then turn off the hydraulic system. The valve must not be under active control pressure from the pump during the setting procedure. Then, you carefully mark the current position of the cylinder rod, maybe with a grease pencil or tape. The seemingly simple step is vital for visually monitoring even tiny amounts of load movement as you begin the precise calibration.
You have a reference point.
Exactly. Fourth, provisional load pressure adjustment. Now comes the delicate part. You very gradually reduce the pressure setting of the counterbalance valve by turning the adjustment screw outwards, slowly. You watch that marked cylinder position like a hawk. The precise moment the cylinder rod begins to move downwards, indicating the valve is just barely holding the load's pressure.
That's the balancing point.
That's the balancing point. You then carefully increase the pressure setting again, turning the screw inwards just until the load becomes absolutely stationary again. This defines your actual load pressure setting point on the screw. A critical caution here from the sources. Do not reduce the pressure setting too quickly. An abrupt pressure drop could cause the load to descend suddenly and maybe even catastrophically, potentially damaging the mechanics, especially if you have multiple cylinders working together.
Okay, slow and steady.
Very slow and steady. The pressure setting in the counterbalance valve tends to rise proportionally or nearly linearly with the spring preload created by turning the screw. So to roughly achieve the correct load holding pressure, you're effectively counting the turns or fractions of turns of the adjustment screw to get to that exact point where it just barely holds the load.
Got it. Find the exact hold point. What's next?
Fifth, applying the safety factor. After precisely determining the number of turns needed to just hold the load, you then add that critical safety margin. You add an additional 30% more turns inwards to that setting. So, for example, if it took exactly 5 full turns out from maximum to reach the point where the load started moving, and then you turned it back in slightly to hold it, you'd note that position. Then you turn it inwards an additional 1.5 turns, which is 30% of 5. This sets the valve to 6.5 turns less than maximum, precisely achieving that crucial 1.3 times load pressure safety factor we discussed. It gives you that vital 30% buffer.
Okay, so calculate and add the 30%.
Precisely. And finally, sixth, secure the setting. This is perhaps one of the most overlooked yet absolutely critical safety measures. Once set, the adjustment screw must be secured against any unauthorized changes or accidental loosening due to vibration. This is often done by sealing it with a lead clum, a tamper-proof lead seal crimped over a wire, or by applying a strong, industrial-grade locking lacquer or thread locker compound.
So nobody can mess with it later.
Exactly. It physically prevents anyone from casually tinkering with a safety-critical setting. It profoundly underscores that this is a true safety device, not something to be casually adjusted or tuned by untrained personnel on the fly.
Wow. That 1.3 times load pressure setting and the meticulous, careful process required to achieve and secure it. That really is a small detail with truly massive safety implications.
It absolutely is.
It makes this component a true guardian of safety, an engineering philosophy of redundancy built right in, rather than just being a functional part that makes things move.
Precisely. It transforms it from just a simple flow control mechanism into an active guardian of safety and overall system integrity, ensuring that even under peak stress or unexpected conditions, control is reliably maintained.
You know, we often hear about hydraulic shock, where sudden movements or abrupt stops or maybe impacts can send jarring forces rippling throughout a hydraulic system. It's like hitting a pothole with your car, but on a massive scale for heavy machinery.
A very good analogy.
Does the VBCD DEA, with all its sophisticated precision load control features, also inherently act as a kind of shock absorber, even if it's not explicitly labeled a shock valve in all its documentation? Is that shock function truly integrated?
You've hit on a really insightful and crucial point there, and the answer is an emphatic yes. It absolutely does function as a shock absorber in effect. While the specific term shock function or shock function isn't always specifically used in every piece of English documentation for these valves, the effect of a shock function is undeniably and profoundly integrated into its core design and everyday operation.
How so?
Well, the primary purpose we've been discussing, preventing the actuator from running ahead of the pump, and meticulously controlling load descent directly and fundamentally mitigates hydraulic shock throughout the entire system.
Okay, so the control itself prevents the shock.
Exactly. Let's break down precisely how it prevents shock. The damping and throttling elements that are meticulously built into this counterbalance valve's internal structure are constantly at work. They don't just regulate flow volume, they smooth the flow changes. They ensure that all movements, especially rapid decelerations, sudden changes in load direction, or unexpected shifts in weight distribution, are incredibly smooth and controlled.
Ah, so it dampens sudden changes.
Precisely. This sophisticated internal architecture actively avoids the sudden, massive pressure spikes that would otherwise occur. Imagine, as you said, a heavy crane boom rapidly decelerating its descent with a multi-ton load. Without this inherent damping provided by the valve, the immense inertia of the moving hydraulic fluid and the load itself would create huge, instantaneous pressure surges, literally like a hammer blow, causing jarring impacts and immense stress on every single component in the system, from the hoses right back to the pump and cylinder seals.
Yeah, you can almost feel that jolt just thinking about it.
Right. But the VBCD DEA masterfully manages this energy, smoothing out the deceleration, preventing those abrupt damaging forces. Our sources, for example, frequently highlight how these valves help operators achieve smooth and controlled actuator motion in demanding environments like construction machinery. And they specifically call out the benefit of reducing shock loads. This isn't merely a convenient side benefit, it is a direct manifestation of its inherent shock-absorbing capability.
So the data sheets do mention reducing shock loads.
Yes, often implicitly or explicitly. By precisely regulating the lowering speed, or Absinkgeschwindigkeit regulieren, as one German source puts it, regulating the descent speed, the valve effectively prevents the sudden impacts that would otherwise generate severe hydraulic shock, which then propagates destructively throughout the entire system. It protects hoses from bursting, fittings from leaking, valves from sticking, and even the structural integrity of the machine itself from fatigue over time.
And are there other benefits to this shock prevention?
Oh, absolutely. The benefits extend far beyond just smooth operation in the moment. Preventing these constant jarring shock loads means significantly less wear and tear on all the hydraulic components. Think about it. Hoses are constantly flexing and being pressurized, fittings are under immense strain, cylinders endure countless cycles of pressure changes, and even the pump itself is sensitive to these pressure fluctuations.
So things last longer.
Significantly longer. By dampening these shocks, the VBCD DEA significantly extends the lifespan of the entire hydraulic system. This drastically reduces maintenance costs, minimizes unexpected costly failures, and cuts down on expensive downtime for repairs. It translates directly to a healthier, longer-lasting machine and ultimately a better return on investment for the owner.
And what about the person running the machine?
That's another huge benefit. It greatly improves operator control and comfort. When movements are smooth, predictable, and entirely free from sudden jolts or that erratic chattering we discussed, operators experience significantly less fatigue, especially over long shifts.
I can imagine. Being constantly jolted would be exhausting.
Exactly, and this smoothness allows them to perform their tasks with much greater precision and confidence. Whether it's setting a precise structural component on a building, delicately navigating challenging terrain with heavy equipment, or even just smoothly and safely lowering a pallet of fragile goods without breaking anything. So, while it might not have a big red button labeled shock absorber, its fundamental design ingeniously achieves that critical function, making every operation safer, more efficient, and definitely more comfortable for the operator.
So it's not a separate add-on or a button you push, but rather an inherent, almost silent benefit of its precision load control. A true integrated guardian for your entire hydraulic system, making every movement smoother and safer, right out of the box.
Exactly. It's an integral safety and performance feature that enhances both operation and longevity, often without the operator even consciously realizing the intricate work it's doing behind the scenes to protect them and the machine.
That's really impressive. Now, where do we actually find these valves in action? You've mentioned cranes and forklifts, but are they used elsewhere?
Oh, absolutely. These valves aren't just theoretical marvels discussed in engineering labs. They are absolutely critical workhorses found across countless industries, performing vital, often unsung functions every single day. Their diverse applications truly highlight their incredible versatility and indispensable importance in modern machinery.
Okay, give us some examples. Where are they hiding?
Well, in construction machinery, as we've touched on, you'll find them everywhere. They are the unsung heroes of heavy lifting and precision placement. Picture a massive excavator boom. The VBCD DEA is critical not just for lifting heavy buckets of earth,
Yeah.
but for the smooth, precise lowering of that bucket into a trench, or for delicately placing a utility pipe without jarring or damaging it.
Right, that controlled lowering is key.
Critical. Without it, the bucket could free fall or lurch downwards, compromising the trench's stability or smashing the pipe. On immense crane booms, as mentioned, they are quite literally the last line of defense against gravity. They ensure that even in the unthinkable event of a hydraulic hose failure, the multi-ton load doesn't plummet catastrophically, but rather descends gently and under control, preventing unimaginable disaster.
You fail safe.
A true failsafe. And on all sorts of earth-moving equipment loaders, dozers, graders, where operators need fine-tuned, consistent control over heavy implements like blades or buckets, this valve ensures smooth, predictable action, reducing operator fatigue over long shifts and drastically improving efficiency, especially on uneven terrain.
Okay, construction makes sense. What about other areas? Agriculture.
Yes, in agriculture, their role is equally critical, though perhaps less obviously dramatic sometimes. They ensure consistent and controlled fluid flow for implements like large plows or precision seeders. Imagine a tractor pulling a multi-row planter across a field. The VBCD DEA helps maintain the exact depth of the plowing blades or seeders, even as the tractor goes over bumps or uneven ground, ensuring uniform planting depth and consistent crop yield.
So consistency is key there.
Exactly. They also help stabilize large sprayer booms, preventing them from bouncing erratically as the tractor moves, which ensures even application of fertilizers or pesticides across the entire boom width, saving costs and reducing environmental impact.
Interesting. What about lifting things more generally?
Definitely. For lifting equipment, from the ubiquitous forklift trucks in warehouses that need to smoothly raise and lower incredibly heavy pallets without damaging goods, to specialized vehicle lifting platforms, the lifts in garages, known in German as KFZ Hebebühnen, that require utterly safe and stable operation to lift cars and trucks for maintenance, these valves are absolutely indispensable. They prevent dangerous, uncontrolled drops and ensure that loads can be positioned with controlled finesse and locked securely.
Okay. Industrial settings, too.
Widely used in industrial machinery. They are foundational components for general industrial hydraulics, particularly in applications involving hydraulic motors, where they provide essential braking and speed locking functions. Think about conveyors, industrial mixers, or even robotic arms that need to stop precisely and hold position against external forces.
So they lock motors in place, too.
Yes, they ensure that a motor, once stopped, remains securely locked, or that its speed can be precisely controlled even when it's driving a heavy, oscillating load. They are, of course, absolutely critical in any safety-critical system where load safety is paramount, especially as we keep emphasizing, protecting against catastrophic load drops in the event of a hose failure on something like a crane boom or an aerial work platform. This is specifically called out in our sources as one of its most vital safety functions, emphasizing its role as a fail-safe component.
It seems incredibly versatile. Any cutting-edge application.
Yeah, looking towards the future, even in the burgeoning field of smart manufacturing and Industry 4.0, there's a significant and growing trend towards integrating electronic over-center valves. These, including the VBCD DEA series and its more advanced electronically controlled forms, can seamlessly integrate into IoT, the Internet of Things networks.
What does that mean in practice? How does that help?
Well, it means you can get real-time monitoring of the valve's performance, the load pressures it's seeing, its operational conditions, maybe even its temperature. This data can be transmitted wirelessly to a central control system or the cloud. This allows for remote adjustments to optimize performance, predictive maintenance insights, where the system can actually alert maintenance staff before potential failure occurs based on performance degradation, and significantly improving overall operational efficiency by maybe optimizing valve settings dynamically based on changing tasks or conditions.
Wow, so the valve becomes part of the data network.
Exactly. It transforms a traditionally passive mechanical workhorse into an intelligent, connected component of a larger, smart manufacturing ecosystem. Very powerful potential there.
That's fascinating. Okay, back to basics for a second. How are they typically installed? You mentioned inline mounting.
Yes, installation is generally quite straightforward due to that design focus on simplicity and reliability for integration. You typically connect ports V1 and V2 directly to the hydraulic supply line coming from your pump or your main directional control valve.
Okay, supply in.
Right. Then ports C1 and C2 are connected directly to the hydraulic actuator. The cylinder ports are the motor ports that you want to control. And as you said, they're universally designed for inline mounting, meaning they fit directly into the hydraulic lines, usually close to the actuator. They act as that crucial intermediary, that gatekeeper, between your power source and your actuated component.
Got it. And what about the numbers? What kind of pressures and flows are we talking about?
Let's briefly glance at some of the typical technical specifications you'd find in the datasheets, which really underscore their robust design and capability. The maximum operating pressure these valves can typically handle is around 350 bar.
Which is very high, right?
Extremely high. To put that in perspective, that's over 5,000 pounds per square inch PSI. So it's definitely built for demanding, heavy-duty applications that require immense force. The standard factory pressure setting for these valves, before specific adjustment, is often around 320 bar, ensuring they come ready for serious work right out of the box, though again, that must be adjusted for the specific application's load.
Okay. What about flow? How much oil can go through them?
Their maximum flow rates vary significantly depending on the specific model and the physical port size. For instance, a smaller VBCD model with maybe 14 ports, like a VBCD 14DEA, might comfortably handle flows in the range of 20 to 25 liters per minute.
Okay, for smaller actuators.
Right. Whereas a much larger model, like a VBCD1 DEA with 1-inch ports, can manage really impressive flows of up to 150 or even 160 liters per minute. This wide range demonstrates their scalability and adaptability across vastly different system scales and power requirements, from small mobile equipment to huge industrial presses.
And those pilot ratios again.
As we discussed, the pilot ratios are generally specified as 1.4.5 or 1.5.5, again, meticulously selected based on the specific model size and its intended flow capacity to ensure that optimal balance of control, stability, and efficiency for different types of loads and applications.
What about temperature and oil type?
Good question. In terms of operating conditions, these valves are designed to perform reliably across a pretty wide range of temperatures. The permissible hydraulic oil temperature typically ranges from about Medica 15 degrees Celsius up to an impressive plus 80 degrees Celsius.
So freezing to quite hot.
Exactly. And the ambient temperature range they can tolerate is often even wider, maybe from negative 40 degrees Celsius up to plus 60 degrees Celsius, making them suitable for diverse global climates and challenging industrial settings, from Arctic conditions to desert heat. They're specifically designed for standard hydraulic oil on a mineral oil basis, your typical HLP or HM fluids.
And the oil needs to be clean, presumably.
Oh, absolutely critical. The datasheets specify an optimal operating viscosity, typically around 30 CSO centistokes at operating temperature, which is a measure of the oil's thickness or resistance to flow. And to ensure their longevity and peak performance, proper fluid filtration is absolutely crucial. They'll usually specify a maximum admitted contamination level using the ISO 4406 standard, often something like 2018-15.
What does that code mean?
It basically quantifies the number of particles of different sizes allowed in the oil. A lower number means cleaner oil. It indicates the sensitivity of these, and really all modern hydraulic components, to contamination. Even microscopic dirt particles can cause wear, valve sticking, and reduce efficiency over time. Clean oil is paramount.
Got it. Clean oil is key. And you mentioned different sizes, like 14-inch to 1-inch.
Yes, the various models commonly available in port sizes ranging from G14 British Standard Pipe Parallel Thread up to G1 allow for incredible adaptability across different system scales. This covers everything from smaller, more nimble mobile equipment to much larger, heavy-duty industrial and construction machinery. Specific product codes you might see, like V0418, V0422, V0432, V0435, and V0436, typically represent different sizes, flow capacities, and maybe specific pilot ratios within this versatile, indispensable family of valves.
The sheer range of applications, then, from the subtle control needed in agriculture to the absolute brute force requirements of a construction site, combined with these really robust technical specifications. It truly highlights why these valves are so absolutely indispensable in so many different industries.
They really are fundamental
They're
components.
not just a component, they're a true workhorse, a silent guardian of both power and precision in the hydraulic world. We've now navigated the intricate world of the VBCD DEA valve, from its fundamental role in ensuring controlled load descent and preventing those dangerous destructive runaway scenarios.
The jattering and worse.
Exactly. All the way to its subtle yet incredibly powerful role in inherently preventing hydraulic shock and guaranteeing overall system stability and longevity. It's truly a testament to intelligent engineering, isn't it? That such a seemingly compact, often completely unseen component can have such a profound and far-reaching impact on both the safety of operators and the operational efficiency of hydraulic systems worldwide.
It really is. And the key takeaway here, I think, especially for anyone involved with designing, operating, or maintaining hydraulic systems, is that in applications with significant pulling loads or overrunning loads, simply holding a load stationary just isn't enough. It's a critical distinction to make.
Holding isn't controlling.
Precisely. You absolutely need active control, you need effective damping to smooth out the movements and absorb energy, and you need that robust, verifiable safety margin built into your system's protection. The VBCD DEA, with its careful design that seamlessly integrates these critical functions, load holding, controlled lowering, damping, and its stringent setting requirements, delivers on all those fronts. It fundamentally transforms what could be potentially dangerous, uncontrolled, and damaging movements into smooth, precise, and unequivocally safe operations. As you said earlier, it's the difference between chaotic energy and controlled power.
So next time you witness a massive load moving with surprising grace and unwavering control, maybe a towering crane arm extending with that fluid, deliberate precision, or a forklift lowering a heavy pallet gently to the ground. Take a moment to consider the hidden VBCD DEA valve, or something very much like it, diligently at work inside.
Doing its job silently.
It's making that remarkable safe movement possible, turning potential chaos into perfectly controlled power.
And maybe it raises an important question for you, the listener, to think about. How many other crucial but often unseen components like this are quietly, tirelessly ensuring the safety and efficiency of the complex machines we rely on every single day? Components that are fundamentally transforming potential chaos into perfectly controlled power, all without us even realizing they're there.